Hello everyone. In this video I like to introduce a tool to you to plan and optimize manufacturing lines. AMS, the Analytical Modeling System, which is based on formulas from queuing theory rather than discrete event simulation. Thus, the benefit of AMS is much faster computation times, especially for large manufacturing lines compared to classic simulation tools. My name is Axel Magert. I worked on AMS more than 30 years ago when we developed this at IBM to model our own manufacturing lines. Assembly lines for storage subsystems as well as semiconductor lines to produce magnetic heads for disk drives. Those lines typically consisted of some 100 operations and roughly 100 product types. And it turned out that it would take forever to do classic event simulation. This was our main motivation to develop AMS. The math behind AMS has been developed by Professor Dr. Thomas Hanschke, who later on left IBM and started to work for the Institute of Mathematics at the Technical University of Clausthal here in Germany. A first version of AMS was written in APL and ran on mainframe computers. Later, we developed a version for OS2 Presentation Manager in C. OS2 went away, and so AMS disappeared. But I kept the source code with me through all the years. And now, after I retired from IBM, I decided to rewrite AMS in Python using WX-Python for the graphical user interface and publish it on GitHub as open source under the GPL license terms. I just wanted to preserve it because I think it still might be useful for someone. Maybe for you who stayed with me so far. Here we go. Let me briefly introduce AMS to you. Let me start to explain what an AMS model consists of. First of all, we have work centers. These are physical work areas on our manufacturing floor. In this little sample model I'm showing here, we see 3 work centers for assembly operations, 1 for inspection, 1 for test, 1 for package, and 2 for rework. The essential attributes of a work center are capacity, specifying the number of servers we have available in this work center, for example, number of operators in the assembly 3 work center, or number of tester available in the test work center. Then another important one is the coefficient of variation of the mean cycle time of all operations assigned to a work center. That would sort of describe the variability of cycle times at this work center. If we choose a value of 1 for the coefficient of variation, this would describe a classic exponential distribution, but we also could specify a value smaller than 1 to model operations which have less variability, for instance, because these are more automated operations. Other parameters for a work center are reliability, mean time to repair, or batch size. Next, we have product types. In this sample model, we have 2 product types, and the important attribute here is a percentage describing the share this product type has in the overall production volume. In our example, our overall production volume consists of 30% of product type 1 and 70% of product type 2. Each product type has its own list of manufacturing operations, and those operations need to be assigned to work center. For product type 1, we have just 6 operations assigned to the 6 work center shown on the top. For product type 2, things get a bit more complex. We see that on the first 2 work center we have 2 different operations, and we also have operations at the rework work center. Key attributes of an operation is the mean cycle time, and also it's possible to model the splitting of a part into many parts or the joining of many parts into one part by using the split join factor. Finally, we have the process flow, which is basically a list of transitions between operations, and each transition has a probability. If the probability is 1, all paths flow from the predecessor operation to the successor operation. As we see, all paths flow from operation A1 to A2, but only 80% of paths flow from A2 to A3. At this point, we lose 20% of paths after the inspection work center, and this is basically scrap we are modeling here in our sample model. The process flow of product type 2 is more complex. Besides scrap, we also see rework loops here in this process flow. For example, 20% of parts go from B2 to operation B7 at the rework 1 work center, and from there they return into the main process flow. And we have another longer rework loop after operation B5, where 10% of parts go to B9 at the rework 2 work center and then flow through the rework 1 work center back into the main process flow. So you can see with this approach you can model any process flow of any complexity you might think of. Let me now show you how the software works. After we have started AMS, we can load a model by clicking on File, Open, navigate to the data subdirectory, and here we can load the sample model which is shipped together with AMS. Once this is done, we see all the model artifacts listed here. On the left in the tree view, we see here all the work center and the product types. And if we expand one of these product types, we also see all the operations for this product type. If I click on work center, I get a list of all the work center with all the attributes. Let me quickly increase the font a bit. So we see, for instance, work center test has 3 workstations, batch size is 1, coefficient of variation is 0.1, reliability is 95%, and so on. If I click on product types, I first see the product mix, 30%, product type 1, 70%, product type 2, followed by a list of operations for product type 1. For each operation we see the mean cycle time, split joint factor, we see also to what work center this operation is assigned to, plus various other attributes. And the next table shows us the process flow for product type 1, all the transitions with a transition probability. So here, for instance, we see parts going from A2 to A3 with a probability of 80%. That means at this point we lose 20% in the process flow. And then it continues with product type 2 operations and process flow. Next, I want to show you the 4 different types of computations AMS provides. Let's first look at the start factor computation. Start factor computation we can do for any of our product types, and we have to specify a daily output here. AMS computes a relative load related to parts we started and a relative load related to parts we ship for each work center. So that means for each part we start, we see 1 part at the first work center, but we see only 0.8 part at the third work center. That's because we have scrap. We lose 20% of parts between operation A2 and A3. Relative to shipments, we need to start 1.31 parts at assembly 1 for each part we want to ship. Again, that's because of scrap. This can be translated into an overall load per hour, per shift, or per day. If we do the same for product type 2, we actually see that the relative load related to parts we start is greater than 1 at the first work center, and that's because of the rework loops. For each part we start, we actually have to process 1.3 parts at assembly 1, because 0.3 parts are returning through rework operation B10. The second type of computation AMS provides is a line and work center characteristics table. This will compute the essential performance key indicators for the entire manufacturing line as well as for every single work center for a given production volume, which we can specify here in terms of arrival rate, departure rate, start of build, that's daily starts, or daily shipments. And the nice thing about AMS compared to a classic event simulator is that it right away can tell us what the possible maximum is. In terms of starts, the maximum possible with this manufacturing line is 219 starts per day. So let's do the computation for starting 200 parts per day. What we first get is a list of characteristics for the entire manufacturing line. We see some parts started per minute and the good parts out per minute. The overall yield, that's a percentage of good parts out for the manufacturing line, is 83%. We run the manufacturing 5 days a week, 24 hours a day. That's actually a model attribute we can specify. We have specified that we want to start 200 parts per day. This translates into 166 shipments per day. Again, we see the maximum here always on the right. The takt time is 8.66 minutes. That means every 8.66 minutes we produce one part. The average line utilization for this production volume is 67%. The raw cycle time 123 minutes. The lead time 284 minutes. Lead time is raw cycle time plus waiting time. And that brings us to the line efficiency of 43%. Parts spend 57% of their time waiting and only 43% of their time getting produced. There's also something like a lead time and efficiency including idle periods. That would include also the downtimes of work center. Work in process is 39 parts. So in average we have 39 parts in the manufacturing line either being produced or waiting in front of a work center. AMS also provides cost modeling, so we can compute manufacturing cost per part, per minute or per day, and also a profit, which here in my model is a negative number because I have not specified any income yet. At this point I can actually show you how to make changes in the model. Let us specify some income for our product types. We can edit the model by doing a right click on any model artifact, which would get us a dialog where we can specify all the attributes, in this case for product type 1, or we can right click here on product types to get us some spreadsheet with all the product types, where I now will specify that my income should be, let's say, $20 per part for both product types. If I make this change, my profit right away turns into a positive number. So now I make some nice profit here with my little manufacturing line. Further down below we have a list of work centers, and for every work center we see the overall load in terms of parts per minute, the net utilization, the total utilization. That's the utilization including idle periods, downtimes basically. We have here the lead time at this work center, the work in process at this work center, the mean queue length, and the 90% quantile of the queue length. This value typically is used to dimension the needed buffer in front of a work center. The work center with the highest utilization here in my model is a test work center, and that's the reason why it's highlighted red here, because that's actually the bottleneck in our manufacturing line. It's the work center which actually determines what our maximum is. And to produce more, we need to resolve this bottleneck. And one easy way to resolve a bottleneck is just to add capacity, to basically buy another tester for the test work center. I can do this by editing the test work center and just specify a new number for workstations. Let's just increase it by 1. Redo the computation, and we right away see the new bottleneck now is assembly 2. And our maximum has improved to 240 starts per day or 199 shipments per day. The third type of computation AMS can provide is a line and work center characteristics plot. This will plot one of the key performance indicators over production volume. Like we see here, the average line utilization over arrival rate. We can change this to start of builds. So if you build 200 parts a day, our average line utilization will be around 65%. More interesting to see is maybe the line efficiency. The line efficiency goes down as we increase our production volume. If we build 200 parts a day, our line efficiency is roughly 55%, so parts will spend 45% of their time waiting. If we would just produce 140 parts a day, our waiting time would be much less. Similar picture we get when we look at the lead time. Our lead time is about 230 minutes when we build 200 parts a day. And we can actually show utilization in lead time at the same time. When I just right click here, it adds the second curve, so we can get all the values from this chart. For 200 starts per day, our average line utilization is 65% and our lead time will be around 225 minutes. Under File Preferences, you can define how many points are computed for such a plot. In this case, currently it is set to 100. That would mean to produce such a chart with discrete event simulation, you would have to run 100 simulations. And you have seen how fast AMS can compute such a plot. Why is our utilization only going up to some value above 70%? Well, remember, that's the utilization, the average utilization of the entire line. When it reaches 72%, our bottleneck will be around 100%. And we can visualize this as well. I click here, I right click on this report and click edit. And let us just show the graph for all the work center. And then we see the blue line. The blue line represents the entire manufacturing line, which is here around 72%. Our bottleneck, our new bottleneck now is assembly 2, which is now reaching 100% when we build 220 parts per day or more. The fourth type of computation we can do with AMS is the capacity calculation. The capacity calculation will compute the needed work center capacities for a given build program. So let's build 300 parts of type 1 weekly and 700 parts of product type 2 and see what AMS computes. AMS computes the new capacity for all the work centers, and we actually see it's the difference to the current model is there's just a small difference, which is we need one more operator in the assembly 2 area. Remember when we did the line that works in a characteristics table, and we resolved our first bottleneck, we ended up with 199 shipments per day. This value here. Now, since we now produce 1000 parts per week, we need to produce a bit more. We need to produce 200 parts per day, and that means we have to also resolve this bottleneck assembly 2, and that's what the capacity calculation has shown us. We need to add one more operator to assembly 2. Yeah, that's all I want to show and say about AMS here in this introduction video. If you like it, just give it a try. And if you have any questions or if you run into any problems, please open up a ticket here on GitHub. Thanks for watching and bye bye.